Well, welcome back. We're here discussing Chapter 2, the chemistry of biology. And I am Susan Forrest, your professor for the semester again. And I am just hoping that this is going to be helpful for you. Chapter 2 a lot of times gives people problems because it's over chemistry and people get freaked out by chemistry, I think. So if you are going into nursing, you are going to need to have some basic foundation of chemistry. And unfortunately, a lot of programs do not require you to have chemistry as a prerequisite. It should, but in the reduction of the number of hours that you need to take prior to your nursing program and to give more time to the actual learning the skills and everything of being a nurse, they've taken out the chemistry requirement. And so if you've had struggles with chemistry before, I hope that this will be helpful for you and that you'll find that it is not so difficult. Some of the things that we're going to be doing, this is not by any means like a chemistry class like Chem 1 or organic chemistry. This is the chemistry you need for biology, and some of the things that we'll be doing we'll be taking shortcuts to be able to help you understand it a little better. And so without further ado, we'll go ahead and look at the first section of the Chapter 2. So Chapter 2 is the chemistry of biology. Before we begin, I would like you to think about, what do you know? So I like to do this before we start any chapter because I want to know what you know. Unfortunately, you can't tell me this because this is a one-sided conversation kind of. But what I want you to do is, before you start the video, I want you to pause and I want you to think about these questions. What do you know about chemistry? What is an atom? What are the 3 subatomic particles? Where are they located? What charge do they have? And what is the mass of each? So if you will stop the video now and then start back up in a little bit after you've answered these questions, just kind of think about these things and try and figure out, what do you know ahead of time. Okay, so hopefully you went back and thought about these questions. If you have not, that's fine. We're going to go ahead and answer some of these questions for you. The first thing, what do you know about chemistry? I can't say what you know about chemistry, but I will tell you that chemistry is the study of matter. Where biology is the study of life, chemistry is the study of matter. And matter is anything that has space and takes up space and has mass. And so this is what we're going to be looking at in chemistry, and everything is made of matter. If a living thing has space and has mass, then it's consisting of matter. It consists of atoms. It is matter. And so what is an atom? And I love like my short little definitions, and so my basic definition for this is the atom is the basic unit of matter. So all of matter is made up of atoms, and atoms are made of 3 subatomic particles. So the 3 subatomic particles are protons and neutrons and electrons. So I'm going to have to erase this to give me more room. And electrons. And they are located, the protons and neutrons are located in the nucleus of the atom, so in the very center. And the electrons are in a cloud, electron cloud, outside of the nucleus. And protons have a positive charge. That is what really defines them, is that they have a positive charge. And neutrons have really no charge, so that's the symbol for null. Electrons have a negative charge, and so to be neutral, you have to have the same number of protons and electrons, so we'll get into that a little bit in a minute. The mass of each is 1 AMU for protons and neutrons, And the mass of an electron is like negligible, so we're going to put Na. It's like 1,836th of an AMU, but that is really not significant, so we don't count it. So when we say the mass of the atom, we're counting the number of protons and the neutrons. And atomic mass unit is basically 1/12 of a carbon-12 atom, or one proton, one hydrogen atom. So there's been a lot of different ways that they define it, but at this point in time, we are defining it as 1/12 of a carbon-12 atom. So that's, hopefully you knew some of that before we get started. And so our learning outcomes for this section are, we're going to look at atoms and bonds and molecules. These are the fundamental building blocks, and so we're going to look at this relationship between atoms and elements and some terminology that are related to this, and list and define 4 types of chemical bonds, and then differentiate between a solute and a solvent, and provide a brief description of pH. So I will just say that this is a very long section. This typically takes me about an hour and a half to get through. So I am not going to do all of section 1 at one time. It'll be broken up into pieces. So the first section is just talking about atoms and bonds and molecules. And so in here, we talked about matter. It's anything that occupies space and has a mass. So it has a volume, and that's what we mean by occupying space. This is volume and a mass. So particles have space and have mass. So that is matter. An atom is a tiny particle that cannot be subdivided into smaller substances without losing its properties. So like I said, it is the basic unit of structure and function of matter. And we talked about the properties of atoms. They have these 3 subatomic particles: protons, positive, neutral, neutrons, and negative electrons. So, and these are found in the nucleus, and these electrons are found surrounding the nucleus. So these are some models of the atomic structure, and you can see the hydrogen atom they're showing you here with the electron shell, and there's just one electron shell, and it is a spherical orbital. It only contains the one spherical orbital. So the maximum number of electrons this shell would have is 2, but because we only have one proton, we only have one electron. And this is showing kind of how the orbitals and how it's spherical, and this is showing it in a different way, with it as a kind of a flat, like a orbital kind of idea, where the electrons just go in a circle around the nucleus. But they really don't just follow a circle pattern. It is 3-dimensional, and it is more kind of like, they call this a p orbital because it has kind of a peanut shape, and it's like an infinity symbol, and they're basically, we know that they are in here somewhere, but we don't know exactly where they are at any one particular time. But just wanted to show you this because really atoms are 3-dimensional. Otherwise we would be flat, and we are not flat. I wish I was flatter, but I'm not flat, and you're not flat, and atoms are not flat. So that's kind of the thing about these models, is that they don't exactly show where the electrons are, because we can't really know where they are at any one particular time. So the elements are an atom with a characteristic atomic structure and predictable chemical behavior. So it's a pure substance that contains only one kind of atom. An isotope is a variant form of the same element that differ in the number of neutrons. And so I think there's really some I words that we're going to be pointing out, and this is one of those words that people kind of confuse a lot of times. Iso means same, tope is kind of referring to kind of a form. So they're similar, but they're not the same. They're the same element, so they have the same number of protons. That is not going to be different, but they do have a different number of neutrons. and so they have a different mass. So the mass is different. And when we talk about isotopes, mainly in medical fields, we're really, interested in the radioactive isotopes because they're used in medical applications, research and medical applications. So they have these unstable nuclei that spontaneously release energy in the form of radiation. So that radiation could be like an alpha particle, or it could be a beta particle, or it could be a gamma ray or something like this, and it could be even neutrons. So these little particles come off, and that decreases the mass of as they are released, and then eventually sometimes they decay into other elements, but they are spontaneously releasing energy, and it's usually identified because you have more than, so like neutrons to protons. Usually it's a 1-to-1 ratio. In most elements, that is going to be the case. But in a radioactive isotope, if it's radioactive, the neutrons to protons are greater than 2-to-1. And so it's greater than, not maybe 2-to-1, but greater than 1-to-1. Greater than 1-to-1. So if you notice, like carbon has 6 protons and it has 6 neutrons, and so its mass is 12. The carbon 12 atom has this 1-to-1 ratio, but carbon 14 has a mass of 14, so it has 6 protons because it's carbon, but it has 8 neutrons, and so that's why it has a mass of 14. And it means that the neutrons to protons are greater. It's 8-to-6, and that would be like 4-to-3, or so it's like 1.3 to 1. So that is definitely greater than 1-to-1. So this isotope is radioactive, because it has more than a 1-to-1 ratio. And so if you look at really radioactive elements, they approach like a 2-to-1 ratio of neutrons to protons. But anything greater than 1-to-1 is, could possibly potentially be radioactive. Tritium, another one, iodine is used. Barium is used. A lot of these are isotopes that are radioactive. So that's one of our first I words. So it's the same element, but it differs in the number of neutrons. So this next section just shows you some of the different elements and their significance in microbiology. And you don't have to memorize this, but I would mention, like here, cobalt is an emitter of gamma rays, and they do use this in treating cancer. They also use it to sterilize food, and so that is one of those that has a radioactive isotope. Iodine is another one, has 131 and 125 atomic masses, and so the radioactive isotopes are used in diagnostics and in fighting cancer too. So like thyroid cancer in particular, iodine is concentrated in the thyroid, and so if you have thyroid cancer, it'll directly attack the thyroid and not affect other parts of the body, which is very helpful. And then some others. Phosphorus has another radioactive isotope that's used in diagnostics. And so anyway, those are just some of the elements and some radioactive isotope examples. So electron orbitals, again, those are the pathways which the electrons rotate around the nucleus, and it represents the volumes of space in which the electron is likely to be found. But again, we can't know exactly where it is found because they're too small for us to be able to, pick out and identify with other particles. They are probably one of the smallest particles that we have in naturally occurring.